inference and thank you. I titled my talk Inference and Representations for Improving the Robustness of SLAM. I promised to come back for sort of a part 2 or a second talk, or to send maybe my former student David Rosen or one of my students Kevin Doherty to do a deeper dive on perhaps some of the inference aspects, which I think will be very interesting to your control group. And I hope this is just the beginning of a conversation. So my group is the CSAIL Marine Robotics Group, MRG. And this is last summer in COVID. My students had been like just stuck in their dorms and apartments, and they finally met up in person. We're just getting back to the lab, which is pretty exciting here. Still like a lot to go. And my ambitious agenda for this talk, but I promise to finish on time, is to give some sense of my kind of personal journey working on SLAM, autonomous underwater vehicles, and self-driving for over 3 decades. Some of the history and challenges of autonomous driving, because it's in the news so much and it's so important for business and society. And it also informs my thinking about autonomy. And then I've been very fortunate since 2016 to work at Toyota Research Institute as a technical advisor in their building an automated driving project and enterprise. And so I want to give some examples from like trying to do it in a company versus a university, what's involved. And so hopefully that will take about half of the talk. I'm going to go fast and then talk about some of our more recent work, a couple recent papers, an ICRA paper and an IROS paper on some, hopefully, techniques to improve the robustness of SLAM. So my personal journey, I grew up in Philadelphia, went to UPenn undergrad, Oxford for my PhD, and then I came to MIT in 1991, 30 years ago, to do autonomous underwater vehicles and joined the faculty in 96. And went through various organizations at MIT, Ocean Engineering, Mechanical Engineering, AI Lab, CSAIL. But for me, the theme has been trying to improve the autonomy and robustness of robot navigation. And in mapping and localization, if you're not familiar, the goal is for a robot to travel through an environment, build the map while concurrently using it to navigate. It's a very high-dimensional, challenging inference problem that with data association uncertainty and lots of interesting representational questions. And I think it's important for the real world, for missions for underwater vehicles and for self-driving cars. And so way back in the beginning, I was very fortunate to go to Oxford in the early days of the robotics research group. This is me in the lab of the basement of the Jenkin building. Actually, a few floors up in the Jenkin building. I had the great fortune to have an Australian lab mate, Alec Cameron, who's, I think, Vice Chancellor in Perth maybe now. And Alec was a star rugby player in Australia. He taught me the rules of cricket and the rules of rugby. And in general, if you go back then, we were trying to use vision. So next to me, this was a computer vision processing board called a DataCube. Actually, it was a New Zealander, Alan McIver, who programmed that to try to do edge detection, maybe 3 frames a second if you were lucky. But we were way too far from trying to do SLAM with vision, which is what we wanted to do. But instead, we use ultrasonic sensors, Polaroid sonars. And in my thesis with my advisor, Hugh Durrant-White, who's in Australia, and I'll say a bit more in a minute about Hugh and his huge influence on me, you know, the goal was to build a robot that could navigate the way that you might navigate at sea using lighthouses or other landmarks for navigation. We wanted to use the features of the world as geometric beacons and use those to navigate. And we used a Kalman filtering framework where we used Gaussians to represent uncertainty and try to use tracking and data association techniques to associate measurements to features in the world. We didn't really do SLAM. I called it simultaneous mapping and localization, SMAL or SMAL in my thesis. And Hugh, a few years later, figured out in a grant proposal that it's much better to call it localization and mapping, or SLAM is a much better acronym for raising money and attracting interest. And Hugh, just a real force of nature. And when he went to Australia in the late 90s, he really, you know, shook things up down there. I had the great fortune to go to one of the best conference experience of my life. Does anyone recognize where this picture is taken? It's pretty obvious. I put it in the caption anyway. This is a historic building at the University of Sydney, I believe. And that's Hugh and I in 1999 at the Experimental Robotics Conference. And just around that time, it's hard to sort of SLAM really came 20 years ago. It really came into force when a lot of people realized that we could make progress on this problem. Things like the SICK laser scanner became available. I put this in for Iman, who, do you recognize where this is? I'm sure you do. At KTH, the first SLAM summer school in 2002. And there are folks in here that I had never known, like Wolfram Burghardt, who's now a dear friend, and students like Mike Montemerlo here. He's the leader of mapping and the localization team at the Waymo Google car team. And we had many feisty debates. This was Hugh Durrant-White and Sebastian Thrun arguing about common filters versus particle filters. And a whole sort of community of people emerged kind of attacking this problem. That's Rajesh Shatila, a real pioneer in the background. And now today, Hugh's the chief scientist in New South Wales, and is has a vision for machine learning and data in Australia, and is very fortunate that I could interact with him. And he's filled me with a love of Australia, which I already had already. But in the big picture, so we want robots that can navigate around the world, underwater robots, self-driving cars. And I divide the problem space along these three different dimensions. So first is representation. How do we represent the environment? And we'd like to use, state space control techniques and inference methods and ways to represent uncertainty, but it's a very high dimensional state space. So we have to think about, if we think, and part of our project that's joint with a number of Australian partners, Iman, Giresh, is to think about how biology might inspire us. The brain has many mysteries, but I think like dense 3D point clouds from LiDAR scanners don't really have a lot of biological basis. And it's really fascinating working with colleagues like Mike Milford, Mike Hessimo at BU, the whole interplay between metrical representations, like kind of coordinate systems, grid cells, place cells in the brain versus topological representations, and the trade-off between dense mapping, which is enabled by modern sensors like Velodyne LiDARs and 3D depth cameras, versus more object-based representations. Can we represent the world more in terms of objects? And really my whole career, going back to the geometric beacons, that was our inspiration in the PhD days at Oxford, is that it should be able to use an object in the world as a landmark and represent that quite compactly. And then there's, so we call semantic SLAM or semantic, just trying to understand the world more in terms of human symbolic terms. And ideally, you have this kind of scaffolding where you go from more metrical to sort of more object-based, and then semantic and labels and symbols to sort of build up a scaffolding towards more higher level human terms. And then there's also the whole allocentric versus egocentric. SLAM is like a pulling yourself up by your bootstraps kind of problem. Or which came first, the chicken or the egg? You need to move to make a map, but you need the map to estimate your motion, and you represent things relative to yourself, for egocentric versus in the world, and how do you develop those kind of world-centered representations? But then coupled in this sort of different degree, we have a very challenging inference problem. And so doing state estimation, and it may seem obvious in hindsight to try Kalman filtering, for example, but this is with a very huge state space. If we want to map, big part of the MIT campus, we might have a state space with a million variables. And we have the curse of dimensionality lurking behind the scenes, because the association of measurements to features and which measurements are spurious and can be ignored is not clear. And so we get a sort of mixed continuous discrete estimation problem. And this is all happening on manifolds that are very complicated. And so, and increasingly, we want to use techniques from machine learning to try to improve inference. And my dream really is robots that get better with time, kind of lifelong learning. What would it mean to create a robot that gets better and better with time? Or even a robot that could navigate around a bit during the day, and then it gets plugged in overnight and it goes to sleep, and it's almost like robot dreaming. It's one thing to learn. How do we learn how do we develop techniques that can forget? Well, how do you know what to remember versus what to forget? And then also, we also want to build systems and make them autonomous. And so this would mean coupling perception to planning and control and closing the loop, and developing systems that we can really deploy, going beyond demos to deployments. And that's very important for us in the context of underwater vehicles, for example, for our Office of Naval Research sponsors. Let's see. So we recently wrote a survey article. David Rosen, my former student, Kevin Doherty, and Antonio, a student who just finished in my group, working in space robotics, where we try to survey a recent just snapshot. And there's so many papers, but we really feel that these themes of inference and representation are places where there's still a lot of great work to be done. And so, a big focus for me at MIT has been trying to do SLAM for autonomous underwater vehicles. And actually, I was involved in an exciting project with John Fulkerson, who's now at KTH, and Morris Fallon, who's now at Oxford, to try to reacquire objects on the seafloor, where, say, an underwater vehicle has a prior map of an area, and then using a lower cost sensor, another vehicle might be able to go back and reacquire targets, features of interest. Processing sonar data and in places where the visibility is really poor. And so over the years, we've been involved with many different AUV experiments, cooperative navigation of multiple vehicles, trying to do ship hull inspection. But it's been sort of a challenging place to try to do spatial autonomy, because it's very easy to lose your robot. Communications is extremely difficult. We need to rely on acoustics. We can only get GPS at the surface. And it lends itself towards this more sparse object-based view of the world, because we don't have the same kind of capacity to get dense 3D data necessarily, perhaps with some multi-beam sonars, but certainly because of the acoustic communication restrictions, having a sort of compact symbolic representation of the world is highly appealing. So I was mostly, my career was trying to do underwater vehicle experiments, and using like robots in the MIT corridors, like Killian Court data set we took 20 years ago, as a way to sort of proxy platforms to test some of the ideas. But I'm going to take a little detour here into the self-driving world. So about 15 years ago, with my dear colleagues, my late friend Seth Teller and Jonathan Howe, we were the leaders of the MIT DARPA Urban Challenge team, which was to build a self-driving car that could navigate in city traffic for DARPA. And it's a very long story. This is our team photo. But we built a vehicle that we tried to make it more driven by perception and using SLAM-like techniques. We weren't able to go like full, just no map, but to have a more sparse GPS waypoint dependency, not to rely on a very like detailed breadcrumb trail, but to have a vehicle, and this is shown here in the upper right, is what we call the local grid map, which is a local representation that traveled with the vehicle, where it would render its perceptual data and try to do the local navigation, say staying in lane lines, and it would evaluate the path planning decisions. So the kind of yellow lines sort of shooting ahead of the vehicle was led by our former colleague Emilio Frezzoli, an RRT star path planner. Well, actually, RRT path planner, RRT star wasn't invented yet, by Sartash Karaman, who's here, to basically try to in real time harvest the perception data and make decisions about the local environment to drive the vehicle safely. For this challenge, the Velodyne laser scanner shown on the top here was an important sensor. In the lower left, this is driving from MIT to Harvard down Massachusetts Avenue. And you can see, if you have a sensor that gives you 1 million data points a second, like the Velodyne, you think maybe navigation should be easy, but it's actually still extremely challenging with all that data, even though we can see with our eyes people and cars and trees and buildings. Making decisions about, first of all, classifying vehicles, et cetera, it was actually extremely hard 15 years ago. There's been tremendous progress, obviously, with visual object recognition. I'll say a bit more about that later. But even today, trying to do prediction, what's going to happen next? How do you sort of handle the dynamic aspect of moving in the world? That's still really challenging. So to make a very long story short, well, let's see. So in terms of thinking about this more systems aspect of building a self-driving car, you want to take your perception data, build the local map, we call it the grid map, and couple it to the motion planner. And in fact, one of my heroes on the DARPA team, Luke Fletcher, is shown here in this hat. Luke is an ANU graduate. He was one of the early students of Alex Zelinsky. He was in the lab that spun off Seeing Machines doing driver state monitoring. Luke was with us for 5 years at Toyota and recently just got a promotion opportunity to Motional with Carl Agnema, who's shown in the back here as the CEO. And in fact, these DARPA challenge photos, like where are they now? Like Ed Olson, his company May Mobility, the guy next to him, Yoshi in shadow here, Yoshi Kawada, is one of the engineers at SpaceX who landed the rockets back on Earth for Elon Musk. And so there's something magical about the DARPA challenges that the people involved, you know, they've gone on and done really cool things. So, but if we think about closing the loop and connecting perception with uncertainty to planning and control in the face of uncertain navigation, you know, it's still a really hard problem. So our vehicle, we had more sensors or computers, end computers than any other team. We had a Blade cluster with 40 cores. It required 3.5 kilowatts to fully power the computer. It was a little bit challenging to manage thermally. We had a 6 kilowatt RV genset in the back to power it and a 2 kilowatt air conditioner on the roof to cool it. And we didn't want to be limited by computation. So to make a very long story short, we finished in 4th place. And a pretty distant 4th place. It was a competition with about 80 teams originally expressed interest. 35 were invited to the final qualifications, 11 qualified for the final race. And there were some sort of incidents along the way. If I had more time, I would play this video. It's a bit fun. I can do it sometime, or you can find it in the app. We had a little collision with Cornell, and they let us continue the race. Well, I'll show you this. What the hell? I'll show you it. This is probably worth, if you've not seen it.
All right, let's check in once again with the boss.
This was about 5 hours into the 6-hour race. That's Carnegie Mellon, who won the competition.
Across the line at the end of mission 2 behind Virginia Tech. Virginia Tech.
So this is Cornell.
Got a little issue.
We had been trying to pass them for about 3 or 4 minutes, and they were having some throttle problems and stopping and starting.
And it looks like the 79 is trying to pass and has passed the chase vehicle for Skynet, the 26 vehicle.
Wow.
And now he's going to, and Thales is going to pass.
Very aggressive. And
Whoa! Oh, we had our first collision. Crash in turn 1.
oh boy, that is, you know, that's a bold maneuver for MIT.
Anyway, so if we were in a room, I would hope at least some of you are laughing. And no one was hurt, and no people involved. But it was an interesting kind of moment in terms of, you know, showing what might happen when you set things loose in the world. And with a robot car, you can replay the data. And so this is our local map. And I'm going to click in a second. You can see Cornell here. We had 3 cameras. Even though we tried to use probably more vision than most other teams, we didn't have a reliable object detector in 2006. Too many, you know, false positives, false negatives. So we relied on the LiDAR. And to the LiDAR sensor, this is just a blob of 3D points. And we weren't smart enough to classify that as a vehicle. And it turned out we had 3 or 4 bugs. They had 3 or 4 bugs. They interacted in a rather strange way that caused us, even though the road was really wide, the route network had asked us to be in single file there, and we thought it was a stationary obstacle, and we tried to pass it. So back in the day, we traded our data logs with Cornell, and we wrote a paper about it. I call it like a 38-page peer review accident report in the Journal of Field Robotics. Not just this incident, but of another incidents. Luke, our ANU grad, was the first author. And if you asked me then in 2007, 2008, it's like we're a long way from a robot that's going to drive on one of the tricky Boston roads like Storrow Drive. Then the field exploded. So SLAM exploded around 1999, 2000. After that conference in Australia, when I had a videotape of an initial SLAM algorithm, and we played it, and Hugh just went ballistic, and he said, everybody start working on SLAM more. And then autonomous driving took off after the DARPA challenge, and Google really surprised us. So just a very brief history. After the DARPA challenge in around January 2009, Google hired some of the leaders from the Stanford and Carnegie Mellon self-driving car teams, and they formed a sort of secret team of about 15 people who for about 1.5 years built a self-driving car and tested it on public roads, and they didn't tell anybody. And one of the New York Times reporters, John Markoff in Silicon Valley, he kind of outed them. He discovered that what they were up to. And it really took the world by storm because we just didn't think you could do this, that you could just test a self-driving car on public roads without telling anybody. But the three visionaries that started it, Sebastian Thrun, who's a sort of SLAM probabilistic robotics pioneer, Anthony Lewandowski, and Chris Urmson, who's now got a startup called Aurora. And I sincerely believe that someday someone will make an Oscar-winning movie about this group of people and what they accomplished. It was just almost magical. What they accomplished and how they did it so quickly. And they just sort of captivated the Google founders, just made this, sustained, I don't know, $1 billion a year for 10 years investment or whatever they've done, and plus. And the potential upside of self-driving is just absolutely tremendous. And so, well, first of all, I got to ride in the Google car in 2014, and I was blown away. This is my student, former student Ross Finman. I said I felt like I was on the beach at Kitty Hawk. We got a nice 20-minute drive around Mountain View and traffic lights and lane changes, and it's like, wow, this is real. The potential upside for self-driving is that safety is what gets me excited to go to work at Toyota. I think the opportunity to use technology to reduce accidents. We can really make a difference if we can figure out how to deploy the technology wisely. And there's over 1 million fatalities worldwide each year due to car accidents. Sadly, the traffic fatalities seem to have risen last year. They just announced today in the US due to COVID. Less traffic, people driving more quickly, and more accidents. But beyond safety, which is enough for me, safety, but you can think about a certain financial or economic transformation where you can increase the efficiency of the road network, change the way people think about time for commuting, where they live. Imagine cities with no parking lots. Imagine almost like a physical internet of goods where things just kind of robotically get moved around the world. Maybe that's kind of happening, with some of the delivery companies. But to be honest, I'm actually have been sort of a contrarian on self-driving, at least in terms of the timeline that it takes. And I have lots of more details. I took about a month of dash cam data driving around Boston. I live in a town called Newton with lots of tricky left turns and traffic situations, and things like trying to make an unprotected left in the US or an unprotected right in Australia, dealing with roads that have been repaved, dealing with snow, not just the loss of traction and reduced sensing range, increased false alarms, but the way that these vehicles navigate or localize themselves is typically relative to an intensity map of what the LiDAR returns or the visual observations of the road surface look like. And if you cover the road with snow, you lose the ability to do localization. And then obviously things like looking into the sun or heavy rain. And in general, I feel there are these really big questions about how do you maintain the maps and deal with construction and changes in the world, handling adverse weather. We need better sensors, better algorithms. But a whole other challenge is dealing with people. So I have these, this example of a police officer that waves me to go through a red light. How do you deal with a police officer directing traffic? And how do you deal with unreliable sensors, despite all the progress in computer vision? How do you handle sort of imperfect detections having false alarms? How do you kind of put it all together in an integrated system? So, and you're probably familiar, I hope, with the distinction between, say, level 2 autonomous driving versus level 4. In level 2 autonomous driving or automated driving, an example of that is the Tesla Autopilot. The human must pay attention at all times and be ready to take over. And the reality is that humans are not good at monitoring an autonomous system. And paradoxically, as the system gets better and better and the human has less work to do, they get less and less able to take over when it really is time that it's needed. But in a level 4 system, the human isn't involved in the driving task. The car does all of the driving. The challenge there is that you go back to this kind of like ROC curve issue with false positives and false negatives. How do you achieve sufficiently reliable detection in challenging perceptual situations that without a human backup, the system can make the right decisions? So obviously there have been tremendous progress at companies like Waymo have an extended deployment in Arizona. There's a wonderful college student named JJ Ricks who posts YouTube videos most days for doing self-driving. Something in the chat here, I'll just check. Oops, I can't see the chat. That's weird. Okay, just jump in on audio if you have an urgent question.
Don't worry, it was my mistake. Don't worry.
Sure, no problem, no problem. So let's see. And you know what I would say is that if you listen to the media, say in 2016, 2017, it was like self-driving is coming in 2020, and it's just a matter of when, not if. But I think that the community has realized now that we've kind of gone over the peak of the hype cycle, and that despite all the big investment, there still are major technical challenges, and there's great opportunities for PhD work. And I think there's opportunities for young professors with a handful of students to just kind of think deeply about components of the problem and make contributions. I have great faith in the ability of small teams to make rapid progress, and in the sort of professors and grad students to really continue to innovate. I think that a company with 1,000 people, it's just a different mindset, and obviously they perform innovation as well, and you have to deploy systems to learn about them. But I think that if someone tells you self-driving is solved, I would say I disagree. Okay, so far so good. Any questions so far? I can't see anything. The way the Zoom's set up, I can't see any faces. So I hope you guys, that's okay so far. So for me, up until around say 2015, I was almost a sort of an admirer of Google, but also a critic, just saying, look, guys, let's not overhype it. But I got really amazing opportunity in January 2016 to join a new effort started by Toyota. And so I at least thought I should, part of this life story is to tell you about my TRI time, because it's been so fascinating and just a different perspective that I think is complementary to my university kind of role. And so Toyota Research Institute was announced in November 2015. Gil Pratt is shown here with Akio Toyoda, the president, and Gil had previously been the director, the program officer in charge of the DARPA Robotics Challenge, which was the humanoid robotics competition to try to do a disaster response scenario inspired by the Fukushima disaster and how we might respond to a future incident. And so Gil started TRI with the vision of really thinking about the future of not just automated driving, but also robotics and material discovery. Toyota has historically been very conservative with automated driving. Part of me is like, people love driving, and even though traffic is a pain in the neck and safety is a big concern, there is something wonderful about a human that is sort of in control of a machine and enjoying using a machine, and we want to keep that human part in it. So I was fortunate to join TRI, and part of an amazing journey from about being one of the first 6 employees to over 300 with a driving team of over 200 people. This is from a few years ago, kind of halfway on our growth journey in our big garage at Ann Arbor, Michigan, where one of our offices is, with Ryan Eustace is our senior vice president for driving. There's Gil Kelly, our executive vice president. And in this group of people, you have, roboticists and machine learning engineers, but also operations drivers for vehicles, people that run the test track, people that annotate maps, people that do all the different pieces that are involved. It's actually quite remarkable. When I was, when I was a grad student, I wrote all the code myself. When I was a postdoc working on underwater vehicles, myself and Jim Bellingham and one other person maybe wrote 95% of the code, Jerome Wagenet. And then in the DARPA Robotics Challenge, we had about 15 people writing code on the vehicle. But then in a company where you have maybe over 100 or 200 people writing code, there's a sort of progression of the roles and what's involved. And it's just really fascinating. And so one thing that I would say is, like, what does it take to build a self-driving car? And so, sorry, let me see if I can. And so we have a vehicle hardware team, a vehicle software team, safety and system engineering. Mapping and localization is a key technology. So being able to locate the car, the sort of geometric location, but also the semantic information about lanes and potential kind of turns and transits and where traffic lights are, and how you might do that, processing perceptual data live and aspire towards a scalable system that can use data to, oops, sorry, I messed this up. And then perception and prediction. So there's obviously been a great progress in how you perceive vehicles and other kind of agents in the world. One of the real magical things is prediction techniques, where you can sort of try to say, is that pedestrian going to continue in the crosswalk? Are they going to, you know, are they standing on the road? Are they looking at their phone? Are they waiting for it to cross? And then coupled to planning and control, which is obviously very critical. At Toyota, and I'll mention a bit in a minute, we have another part. This actually goes back to the Luke Fletcher, Australia National University, Alex Zielinski, understanding the driver. So having driver monitoring coupled to the outside world to do what we call driver risk assessment, where you try to ascertain for a human-driven car, what is the intent of the ego driver and how does that interact with the perception in the world. Machine learning is absolutely critical these days to have a state-of-the-art system based on massive amounts of data. Simulation is absolutely critical, how you can test code when you change it, and then deploy and say safe closed course testing, and then supervised public road testing. There's massive amounts of data is captured, processed in the cloud. The user experience is very important, how you can sort of present the information to the user and build trust. And then how you have safety drivers that kind of put this all together into an operational system. So it's just been mind-blowing to be part of such a big effort, where you think about the scaling that happens when you want to get to something that's more towards deployment in the real world. So at TRI, we've had an evolution of robot platforms. And just briefly over the years, we call it platforms 1, 2, 3, and 4. Progressing from the more sort of science project, university lab, DARPA style with 80/20 and strapping sensors on, with Velodyne's progressing to using the Luminar LiDAR and coupled more sort of stylistically into the vehicle. And so if you'll indulge me to talk a little bit more about this, the TRI work, let's see. Well, let me just say, the thing that sets us a little bit unique is we're trying to create one system that has two different modes of operation. So the chauffeur mode of operation is the level 4 type system, where the system is fully autonomous and the driving system is engaged at all times. This will be perhaps for like a mobility as a service application in limited areas, expanding over time. But in addition, we have a vision for something we call Guardian. And in Guardian, the goal is think about it as it's an active safety system, but that uses all of the tools of robotics, of perception, planning, control under the hood to try to get the benefits of autonomy for a human-driven car. So the philosophy of Guardian is that the human should be always engaged, but the vehicle is ready to jump in and take over. And if you could just stay on the road, don't hit things, don't get hit, using all of the tools that we have as a community, as roboticists, my hypothesis is that we could dramatically reduce traffic accidents. So we've been testing both systems, and our hypothesis is that a lot of the core perception, prediction, and planning algorithms are actually shared amongst the two different applications. And so just to give you a little taste, we have this sort of historical timeline. I'm just exhausted thinking about it, but like 5.5 years of work on this technology. And we've been building towards the Tokyo Olympics, which I'll mention in a minute. So I'm going to give you one Guardian example and one chauffeur example. The Guardian example is an initial concept demo we did back in 2017. And we created a vehicle with 2 steering wheels, which may seem a little bit crazy. Why would you want to have 2 steering wheels? Well, the idea is that we could have a safety driver in the left-hand, US left-hand drive seat, have the autonomy system, and then have a driver that's being kind of protected by the Guardian in the right-hand seat. And so this is on a closed course test with a driver monitoring system. And I'm going to play just a short video clip with Gil Pratt narrating, Ryan Eustace driving, Luke Fletcher from ANU's in the back, and I'll play this. And you can get just this is a little glimpse of our vision for Guardian, in which we tell Ryan to fall asleep.
Now we're going to demonstrate our Guardian system. We're going to emulate what happens when a driver falls asleep. Guardian can tell by using a camera that's part of the dashboard. The camera can even see through sunglasses in order to see what the driver's eyes are doing, or if their head is moving into a position that indicates they're not paying attention. So Ryan, whenever you're ready, why don't you go ahead and pretend to fall asleep. And now Guardian has stepped in, it's driving the car for you, and now it will offer at some point to give it back to you. Why don't you go ahead and take it now?
This video has one more example. I'll just play it.
One of the most frightening things that can happen on the highway is when a car in front of you switches lanes to avoid debris. You have very little time to react because your view is blocked by the car in front of you. We have sensors that can see significantly better than a human driver can see. The Guardian is going to take over where a car switches lanes in front of us in order to avoid debris. Here, that car switches lanes, Guardian decides we have to switch lanes also, and we avoid having a crash. Now Guardian has offered to hand back control, and Ryan has taken control back of the car. So today you've seen demonstrations of two basic technologies that the Toyota Research Institute is doing research on. This is all part of TRI's work to eventually build a car that can never be responsible for a crash, regardless of what the driver does.
So the vision is a car that can never cause a crash. On the chauffeur side, we had been working towards an Olympics demonstration in summer 2020. Obviously, the last 18 months, last 15 months, the world has been turned upside down. We've continued this effort, and we don't talk too much about our work publicly, but we've publicly shown just some little glimpses of our testing. And so in a neighborhood of Tokyo called Odaiba, which has a lot of heavy goods vehicles, so it's quite challenging, we have a scenario where you want to do level 4 autonomous driving. We have large vehicles. There's a lot of parked cars that block lanes, buses. You need to give way to pedestrians, but you also need to share crosswalks appropriately with pedestrians to not delay traffic. You want to obey traffic signals, deal with complex intersections, and lots of merging and splitting lanes, lane changes, narrow lanes. And of course, you want the robot the car to drive smoothly, not more like a human than a robot. And so I'll just show you a little glimpse of sped up view of one of a circuit on a time when traffic's not too busy at this point, but just showing you the UX display on the right to the user, and then a camera view on the, so UX display on the left and a camera view on the right. Under the hood here is just a phenomenal amount of work to do all the different components I talked about, data processing to do machine learning for detecting vehicles, localization, mapping, controller development, and some of the more challenging aspects relate to the prediction and the associated behaviors. So when you can choose to borrow a lane, how do you sort of share a crosswalk with a pedestrian? There's a whole almost social ballet of driving that is surprisingly complicated, and it gets harder. Just pick the time of day when there's more and more people, you can up the difficulty level. So it's really been fascinating to see, and I just wanted to share a little bit about that. And let's see, how am I doing? Any questions so far? I'm gonna kind of pivot back to the more academic university research part, but any questions on the driving piece there? We'll just keep going. Okay, and feel free to shout out at any time. Okay, so let's see. So if I'm going to pivot back to my life as a professor, and my group of students and I, so I'm going to use some of the slides that we showed at our recent Muri review, and then one sort of older work from last year. And ICRA's happening this week. We have one TRI paper and on prediction and 3 MIT papers. I'm actually choosing to present a paper that we've submitted to IROS. We're still waiting on the review results, and then a paper from last year's ICRA. And so going back to this issue of the sort of spatial understanding at the level of objects, I kind of feel that one of the real challenges in terms of answering questions like where am I and what's around me is dealing with ambiguous situations. You know, how do we, if we have a coffee cup, we can't see the handle. Maybe this one has a nice pattern, but maybe, or a lot of times you might have a robot in corridors. A famous example from Dieter Fox from 20 years ago is is a multiple door problem. Which door am I looking at? So I think one of the fundamental questions here is how do we handle multimodal uncertainties, so non-Gaussian uncertainties, for example, and how do we handle ambiguity? So just to lay a little bit of the groundwork, I want to show some work from my student Kevin Doherty, who's been a real leader in our research group, especially during COVID. And there's a link here. I'll share my slides to his 10-minute ICRA presentation last year. Does a much better job, I think, than I can just here to just sort of give the context for this work. But we humans, sort of seamlessly incorporate this kind of semantic understanding of the world. If you're familiar with the Boston-Cambridge area, MIT is in the right here. Stata Center is where our lab is. This is one of the canonical MIT dorms. It's called Simmons Hall. It's called the Sponge, is the nickname the architect gave it. He was inspired by a sponge in the shower. And you can walk past Simmons and cross the BU Bridge and get to our colleagues at Boston University. If you think like how you give a human direction in terms of just a few landmarks and easily recognizable things, we believe that machine learning should make it possible that robots could navigate in similar ways than you might just sort of give visual landmark directions to a robot. And in particular, it resonates with our desire. Kevin's in the MIT Woods Hole Joint Program to do underwater robotics. And so as I mentioned earlier, the sparse representations, I think, just really resonate with the underwater application because of the limited data transmission and just the dynamic nature of the environment. And also the high cost of failure leads you towards wanting to have quite a great level of robustness if possible. And so, but the challenge is that models aren't perfect and learned perception models fail. And so this might be a little bit of an unfair test, but this is Kevin taking YOLO, just kind of off the shelf detector in his house. And this is one of the still frames of it, but I'm just gonna, it's funny that I don't think computer vision researchers, as often as I might like, just take an algorithm and run it around the world. I think that's where robotics can really help. And Kevin just said, what if I just turn on YOLO and walk around the living room of my apartment? And obviously, chair or sofa, that's great. But if you think about a robot doesn't necessarily know which detections to believe and which ones to not believe. And here, YOLO's thinking that the guitar plus the chair is a person, and obviously it's not a person. Or it might think that the remote is a teddy bear at one point, I think, in this video, or the juggling balls. And so, if we want to deploy either underwater robots that are hard to recover when they get lost, or self-driving cars navigating in downtown Sydney or downtown Berlin, we want to have high integrity systems. And so how do we create systems that are robust to that? So our hypothesis is that with semantic SLAM, we can try to get a higher level of robustness by using the machine learning kind of detections in a larger context that thinks about location information and objects. And the idea is that objects should help you to navigate, but location should help you to better understand objects. And there's this kind of give and take between the object and sort of location information. So we can basically set up the semantic SLAM problem where we're trying to maximize the probabilities on a state space where we've got robot poses, detections, and then data association decisions. And for example, in this paper, Kevin used the KITTI data set with cars as landmarks. You probably don't want to navigate with specific cars as landmarks, but it's an example to try. The challenge with setting this up with the discrete decision variables is that the number of hypotheses is going to grow exponentially. And in fact, I feel like I've been trying to do multiple hypothesis tracking my whole career. Back in 1988, I got the Yaakov Bar-Shalom and Thomas Fortman book, Tracking and Data Association, and it really kind of changed my life because I just said, this geometric beacon problem we can attack as a multiple target tracking problem in a sense. So there's a large body of related work, and for time I'm going to kind of go a bit too fast here. But the classical approaches that do a maximum likelihood data association, I would say that they led us to having some cool videos, even 15, 20 years ago of working SLAM systems. But I would claim that they're brittle and they're error prone, and so there have been a lot of work on robust SLAM. And in fact, the Olson Argwell Max Mixtures paper, I think it might have been from the Sydney 2012 RSS conference. And, we're building on that work. And then obviously probabilistic data association Nikolai Atanesov at University of San Diego has done some outstanding work. And I think that we're trying to basically combine techniques of robust SLAM with data association and semantic SLAM. And so our approach is, our claim is that our approach, by using a mixture models with a max mixtures approach, that we can avoid the sort of exponential complexity that grows with an explicit hypothesis enumeration method. And so our sort of language for attacking these problems is we use factor graphs. Frank Dellert's work at Georgia Tech has been very inspirational to us. Michael Case, one of Frank's early students, was a postdoc for many years with me and is now a professor at Carnegie Mellon. And we use ISAM, the sort of ISAM incremental smoothing and mapping framework. And the goal is to use sort of factor graphs as a language for representing robot poses here in X and landmarks L and data association decisions, and to try to basically be able to reason with mixture models on factor graphs and try to do that in an efficient way. So, so effectively, our approach is kind of hypothesizing when we get a new measurement that it might be either a new feature or it might be a known feature. And these kind of things we were doing in Kalman filtering frameworks, you know.
If the measurement corresponds to one of the known landmarks.
Oops, that shouldn't have happened. Sorry. I think that I somehow got the wrong. Okay, good. Okay, I clicked the wrong button. And then, so our approach, effectively, we're trying to reason on multiple hypotheses on the factor graph model. Okay, so let's see. So let me show you an example. So this is work that we published at ICRA 2020, and it's sort of like a starting point for some of our work on the MURI. And there's always a question of how do you do real-world experiments that sort of show enough of an idea to give you some demonstration of feasibility, but it's not either so unrealistic that it's not sufficiently compelling, but it's also not so much like kind of work in terms of a big deployment. And so for that paper, we used MIT race car robots, and we deployed April tags, the kind of fiducial markers that Ed Olson developed after he left MIT. And the video goes very quickly, but the basic idea is that we're just deploying April tags, and we actually use the tags with a contamination probability, and we have kind of multiple ambiguous classes, and use it with a 10% misclassification rate, and then add some extra odometry error. And what this video shows is comparing the different approaches for some tricky kind of loop closure scenarios, and comparing how our approach does with the max mixtures. We have two variants, one with and without using a null hypothesis, which is that a measurement is spurious. And in general, dealing with outliers is one of the sort of challenge areas for the future, but we outperform a max likelihood approach. Okay, so how are we doing now on time? So I think I don't want you to miss your lunch, I guess, right? It's coming next. So it's about 5 minutes to noon. How's it going?
Yeah, we have 5 minutes to go.
Okay, so so my last 5 minutes, I want to talk about, this is the IROS paper that we submitted, and this is trying to generalize this approach towards systems, situations with greater ambiguity. And this is very much a COVID project. And so actually during COVID, my wife and I started playing cards every night after dinner, you know, just sort of like a sanity kind of thing. And I've got a deck of cards in my hand here. And so I was thinking of ways, how can my grad students stuck in their dorms do interesting experiments that help us advance our algorithms? And it may seem almost trivially simple, or maybe not even ill-posed, but if you take an object that has this ambiguity to it, you could develop an explicit representation that represents that. But what I would like to do is to have a robot that can understand many, many objects in the world and handle lots and lots of ambiguities. And it turns out that just simply the flip ambiguity of a playing card is enough to kind of trigger a failure in a typical SLAM system. So in general, we're trying to extend the approach to deal with objects with ambiguous poses. I'm just going to quickly flip through kind of some of this part of the talk. But the long-term goal is a situation that is much more tolerant of ambiguities. A lot of our algorithms, to be honest, are a bit fingers crossed that when it works, but if it makes a mistake, forget it. And we want systems that are more resilient. And so systems that can tolerate ambiguities. And traditionally, this is from the Sedena et al. Survey paper of SLAM a few years ago that I definitely recommend. This sort of front-end, back-end decomposition where you might do maximum a posteriori estimation in the back end and then do feature extraction and data association in the front end. What we're working on is ways where we can kind of couple those front end and back end processes, where instead of just making hard thresholded decisions in the front end that we know are going to have some mistakes, that we can pass multiple hypotheses from the front end to the back end and have a back end that is more tolerant of the ambiguities that we have in our perceptual data. And just to give you a very quick example here, I'm going to show you so we're extending the max mixtures, and the key thing in this paper is we're adding what we call a dynamic reinitialization, whereby if the algorithm thinks it's made a mistake, it can kind of do a sort of a backtracking and do a sort of a surgery on the pose graph, and then sort of basically jump to a different mode. And so, sorry, I'm going too fast here, but the sort of foundation is factor graphs and the underlying non-linearly squares. If things are Gaussian, we have quite a good understanding as a community on the problem. But the problem is when we have the sort of discrete ambiguities from data association or this kind of pose ambiguity, it tends to break existing methods. So what we're working on is effectively using the mixture models and extending it to try to be more robust to handle ambiguities. And so the way we're doing it is to sort of effectively, it's almost like a backtracking approach where you can, as the hypotheses unfold in time, that you have a capability to sort of go back and revise other decisions. So obviously we're sort of skating on the edge of computational complexity here. You always have to fight the kind of blow up of hypotheses, but we've had good fortune in the experiments we're doing so far, and we're continuing trying to do some more theoretical analysis to understand the computational properties. Let me just give you a simple example in my last method to kind of show you this, and I'm happy to send you the paper if anyone wants to find out more. I should come back and give a better talk with more of the technical depth on the recent research. But the basic idea is to do this kind of surgery on the factor graph to be able to backtrack as decisions unfold, to as new measurements disambiguate prior decisions, to go back in time and try to sort of effectively correct those decisions. Or another way might be think of looking at it, looking for a consensus over time. And so the idea I came up during COVID of using playing cards, I don't know if you're familiar with the game called 52 card pickup. It's certainly where you just throw 52 cards in the air. I would like a robot that could do 5,200 card pickup. And so if we have multiple instances of the same objects, you know, like 2 Jack of Hearts, this would actually confound a typical SLAM system. So we just came up with a very simple experiment to sort of try to show the concept with a small robot navigating in an environment with a mocap to do a sort of a ground truth. And we trained a detector. It's surprisingly hard to get a very good playing card detector. It's fine if you hold it at a good angle and so forth, but for like varying angles, but this is just a bunch of cards thrown on the, placed on the ground. We'd kind of made it a bit orderly. And this is a little video that shows reprocessing. And the point of this, and it, in some ways is an artificial straw man, we're being a little bit unfair, but you know, without the ability to deal with the ambiguity, if a single hypothesis system basically sees an object thinking it's coming from the north and it's actually coming from the south, your estimator is going to blow up. And in general, you know, the famous Australian roboticist Rodney Brooks, who's been a huge kind of pioneer and figure in my mind, Rod Brooks from Adelaide, you know, he said, you know, he likes to look at the assumptions that people are making and break those assumptions and see what happens. And so let's see, we have another example with some simulated coffee mugs, but just to give you a sort of an example here is that find how an existing algorithm can break and find a way to make it not break, and hopefully in a way that's generalizable. So, okay, so I think I got to wrap up here. So the summary, you know, we're adding sort of this pose ambiguity awareness and object-based SLAM. And there's a lot of interesting potential work on the inference side under the hood, and then hopefully coupling that back to active SLAM to make decisions to best resolve ambiguity. And so we're working on adding in data association mistakes and coupling to an active path planning. And then the final, you know, couple advertisements is we did this recent survey paper to try to give lots of kudos to the broader community thinking about these sort of sets of questions of the last years. People like Luca Carlone and David Scaramuzza, and wonderful community out there. And then I definitely want to point you, I found a talk of David Rosen's online at the University of Toronto. And David's thinking about how to take sort of insights from non-convex optimization and duality to come up with certifiable solutions. One of the challenges is that you don't have a robot. A robot out in the world doesn't have a human that's helping it to know when it makes mistakes or not. How do we create systems that are self-certifiable, that know what they know and know when they don't know, and avoid failures and overcome and recover from failures? So, okay, so I'll stop there because I think it's just about time for noon there, and I'm gonna make my screen, the PowerPoint, smaller so I can see some faces, and let me know any questions if you have time.
Thanks, John. If there is any question, I can ask a quick question myself. When you wanted to talk about bringing Active SLAM into it, and with the performance metric of disambiguating the previous decisions, do you have some gut feeling what that measure of disambiguity might look like? And
yeah, that's a great question. I think, for example, mutual information has been proposed as one technique for Active SLAM. For example, some interesting work from UPenn in a different context, Max Likachev, I think, and Vijay Kumar. I think you almost want to, this is not a direct answer, but I have a colleague at MIT from Brain and Cognitive Science and CCL, Josh Chenenbaum, who talks about analysis by synthesis, and almost like, imagine if your robot had like this really good prediction engine that it could simulate the future activity of the world, almost like generating fake perception data, and just run, like almost like the way our DARPA challenge did, is run 50 different hypothesized futures and pick the one that best maximizes the objective function. Could you have almost like a forward simulation that's always running in the background, and it's basically pre-computing what you would expect to gain, and then choose the best gain. The challenge is, how does that does it get stuck in something that's kind of local, and how do you model the unexpected? So based on what you know, it's pretty easy sometimes to predict, but how do you model the potential to find out something you don't know, if that makes sense?
Thanks. I mean, this is really a very fascinating question. I've been thinking about it unsuccessfully for some time.
I'd love to talk more about it, and my students are thinking about it too. Yeah.
So, is there any other questions? If not, let's thank John again for the great talk. I'm looking forward to the follow-up talks that he or David Rosen might be giving in the future. Thanks, John.
Okay. Oh, thank you. My pleasure.
Thank you, John.
Well, thanks, Girish.